Hey everyone, welcome to this year's version of the Untold Stories. So I'm just going to start off just to explain a little bit about what it is because we've changed the names a couple times, and ultimately, you know, our industry is just like a lot of other industries where we have a big generation gap. There's a lot of knowledge, a lot of guys could be retired already, but they're not. So before they're gone out of the industry, we're trying to get some of these stories and stuff that, you know, the mouth-to-mouth stories, we really have to know the people to hear them actually recorded on video. So that way in the future, you know, people can still access these videos and see the stories. So like, for example, the idea is to do it about methodologies or tools or anything that we use in the industry on a daily basis, you know, where that came from, what's the history of it, and then what's the future of it. So like, for example, the first year we did it on blast vibration regulations and how those originated and from the guys that actually wrote the study and how they're actually applied in regulations today. So that's kind of an example. So this year we got two good topics. One, Alastair Torrance is going to talk about detonation velocity, and then Tom Palangio is going to talk about fragmentation analysis. So we kind of decided to go with an equipment, history of a couple of tools or pieces of equipment that we use in the industry, a lot of us on a daily basis. So with that being said, it's not about me, but I'm going to be in this new format. Pedro's idea is kind of like a late night talk show type of thing, kind of a panel discussion. So I'll be up here asking a couple questions, but this is a pretty laid back, low key thing. So we'll open the floor to questions from you guys as well once we get through our bits. So with that being said, I'd like to welcome Alastair Torrance up to the stage.
Excited to be here.
Shake the hand.
Yeah. So I guess I'll sit down, get comfortable, and probably say, well, why the hell am I sitting up here in front of you talking about these things? And I'll just give you a little bit of history. So many years ago, I started working for BHP, and at that stage, we were working in a corporate research laboratory. The company was dissatisfied with the amount of information it was getting from its explosive suppliers about how the explosives were working at their mines. So we were fortunate, and they decided to fund a blasting research group. And one of the first things we did was figure out how we could measure various things in blasts, and one of those was VOD. So we actually started making some VOD equipment from scratch, and we'll talk through that a little bit later on. So that's why I'm here, sitting here talking to you about my experiences with VOD.
Great. So you the first question we had, we got a few questions written down. The first one we had is why we measure VOD.
Yeah, so I guess, has that gone up there? Yeah, it's a good question. Why do you measure VOD? Well, you deal with a bunch of engineers, don't you? And engineers always want to measure something. And I guess it's something that can be measured in this very rapidly occurring reaction. And there's a picture of a cartridge firing. It's courtesy of Diana Bell. Those things take a fraction of a millisecond to detonate all the way through. So you've got to have got to be really quick to try and capture it. But some of the things that you can measure from there, if you measure the VOD, you've got to do it with, you can't use a stopwatch or a calendar, obviously. You've got to use some high-speed data acquisition in some way. And then there are some things you can do with VOD. You can make some estimates of the detonation pressure of the product. There is a loose relationship between the velocity of detonation, how fast it's reacting, and the density of the product to give you then some information about, well, will it be good for hard ground or soft ground, or how this product might best be used. And how it might break the rock, how it might produce the fragmentation that someone's going to come along and measure a bit later on. And the first thing that you've really got to get across is velocity of detonation is dependent on the product, dependent on the formulation, dependent on the diameter of the product, dependent on the density, dependent on a whole heap of things. So to quote a single number for VOD is probably a little bit misleading. All it's doing is giving you a general idea. And it gives you an indication of the completeness of the chemical reactions that go on in that bubble there. So I guess those are some of the reasons why we measure VOD.
Yeah, I think there's a lot of equations out there, at least I've used a few that use VOD to calculate detonation pressure and things like that, so it's useful information. So how exactly do we measure VOD?
It depends if you're going to be in the laboratory or out in the field. It depends if you're in the 1900s or the 2000s. If we go back and look at some of the more earliest ways of doing it, initially, one of the very first ways was to use something like this, which is a streak camera. Very high-speed rotating plate that puts an image of a detonation as it occurs across a film, and you end up with something like this, which looks pretty messy, but that's a VOD. It's basically the slope of that line, because you know how fast the film's rotating. The slope of the line gives you the velocity of detonation. As you can see some, I guess, some irregularities in some of those due to either product not detonating quite correctly or changing product. Clearly, something like that takes hours to set up, probably several repeats to actually make sure you capture a film, an image, and then you've got to develop it and you've got to analyze it. But that's how the velocity of detonation was first being measured, 100 plus years ago. And you can do it in other ways. You can look at, so this is looking at sideways on, and the one on the left is basically the end flame from an unstable detonation. So the detonation hasn't really gone very well, but you still can see the byproducts coming off. And the one on the right is a stable detonation. You can also, if you look very closely, you can see there's a slight curvature on that. That's because it's a non-ideal explosive, and it will detonate up the middle slightly faster than it will at the edge because it's losing energy at the edge. Another way of looking at it is to take a series of frames, very, very high speed. So this is a primer, and obviously you've got a distance there, you've got a grid. You can see where the shock front is in each of those frames, and you can then calculate a velocity of detonation. Not very practical for a guy like you underground, covered in muck and everything.
Lighting's not too good.
But very much understanding the detonation and the detonation physics of in this case, it's a primer. And you can see, this is done in water, so you can see the shock waves going out, and you can infer various things out of that. So that's one of the ways that was done, I guess, without putting anything in it. The second way that's been done for years and years and years is a thing called the Detonation method. Now, Mr. Detonation was a guy in the early 1900s, and he figured out that if you put some detonating cord a known distance apart into a cartridge, the detonator fires, the cartridge starts to fire, it hits the detonating cord or fuse, and that fires, and then the cartridge continues to fire up the end, and it hits point B, B fires, and that detonating cord comes together, and where the two shock fronts come to collide, you actually get a mark on a plate. All sounds pretty fanciful, doesn't it? Sort of. Yeah. Does it actually work? Do people actually use it? Well, the answer is yes. This was I was up in India a few years ago, and this is how they test the quality of their product. They get a piece of detonating cord, and down at the bottom, that white thing is a piece of aluminium plate, and they've got a known distance apart, and they do their QC using something like that.
So I suppose the assumption is the detonating cord has a constant velocity.
Yeah, you've got to make that assumption that there's a constant velocity, and you're getting repeatable results. So here's just 3 of them set up, and on the right, where those, you can't really see on this image, but those pink ovals are where the detonation actually collides. And not only are you relying on the detonating chord, you're also relying on the, I guess, the accuracy of the tools used to measure it with, because you're basically using a steel ruler to measure a tiny little thing on there. So it's, and you can see it's used in the field. But again, it's not down a hole, it's just a cartridge sitting on the ground. So that's a way that's been used. Just as an aside, there are other ways you can use this method without using detonating chord. And that's kind of fun. If you're out in the field and you have a cartridge of explosive that you got some concerns about, you can use exactly the same method with a shock tube. I've got a couple of other examples of this just being used normally. But if you use shock tube, you get exactly the same effect, and you can actually get easily get multiple points up a cartridge, because the shock tube fires, and when the next one comes along, and in that Detonation method, where they collide, they actually blow out the shock tube. So you get this nice measure of where you can. So I've done that in a test we were doing actually in the middle of Sydney. We did a test with a little charge, and we wanted to know what the VOD was, and the simplest way to do it, because we had nothing else, was just use some shock tube, and we got some good results. So this is the sort of thing you see. You can see it's quite clear where the shock tube has blown out. So that's sort of older time way of doing it.
Yeah, and surely we've moved along from that with newer technologies and methods, right?
You mean you don't do this?
Well, like you said, underground, like.
Yeah, of course we have, and people are, now this is not working.
Yeah, I think the biggest question is, how's it actually performing in the blast hole?
Yep, and if the clicker would work, I could show you.
Ooh, technical difficulties.
Technical difficulties. Oh, is that the next? Yeah, okay. So again, yeah, obviously we can now start using electronic techniques, using basically a circuit, a sensor of some description, mostly twisted bell wire, put them a known distance apart. Clearly, when the detonation front hits the first one, you actually get a signal coming out due to the plasma that's going past, starts a counter. The second one stops the counter, and if you know how far apart they are, you can measure that. So it's got it here. Looks like it's on the bench. Looks like it's like the Detonation method, but in fact you can put that down a hole, and you can get a measure of how long it takes the explosive to react between 2 points. So you can get an average VOD for that length. Then if you want to go a little bit further, you can put multiple cables down and have multiple start-stops on the timer and get a bit more information. Another thing you can do with this method is you can actually look at the curvature of the shock front. Now, that's probably not something people do every day, but if you are developing an explosive, you might be interested in how close to its critical diameter is. And the closer it is, the critical diameter, the more curved the shock front will be. So you can gather information about that sort of thing using that technique. It's frozen on me again.
He's got it. We've got good IT support.
Yeah. Are we going to move forward? Oh, went forward too far. Another way that you can use a counter is now start using fibre optics. So that blue loop is fibre optic sort of looped in and out a known distance apart. And you're going to end up getting a series of pulses of light as the detonation front goes past those. So again, measuring the speed of those, you can get a graph like this, which will give the time along the bottom and a signal at the top. So if you know how far apart they are, you can quite easily measure the velocity of detonation. And you end up with something like this, which is starting to approach some things that we talk about being a continuous VOD, but again, it's just discrete points that are going off one after the other. If you want to take it a little bit further into more continuous VOD, because I know you're going to ask that question. Yeah. Some of the methods that people may have heard of are something called Cortex was its original name. This is basically time domain reflectometry. So a pulse goes down a cable, it meets a discontinuity, it's reflected off the discontinuity, and the time it takes for it to go down and come back up is measured. Obviously, as the cable gets shorter, the time gets faster, and you can calculate the velocity of detonation or the rate of change of the cable. And you get stuff like this, something that I guess we're more used to seeing and you'll be more used to looking at from underground measurements or even open pit measurements. But all this stuff came out of the nuclear industry in the sort of the 50s when they were looking at yields from nuclear detonations, how fast the shock wave travelled, where it travelled, those sort of things. So they did a lot of studies about cable strength and things to measure the different pressures that are generated. But it's all the same technology of firing a signal down and waiting for it to come back up, echo back up the line. And this is a much more up-to-date version that you'd be very familiar with. A nice little compact thing that's not much bigger than in the good old days you'd say not much bigger than a couple of cigarette packets, but I guess no one knows what those are now, so it's not very big. And that has all the measurement technique and capability to do this time domain reflectometry. There are other methods, of course. One of the things that we got involved in BHP was looking at a thing called SLIFER, and SLIFER stands for the shortage location indication by the frequency of electromagnetic resonance. So it's one of these acronyms that seems to have been cobbled together to make something that's kind of useful. The nice thing about this is it's a really elegant technique. The frequency of an oscillator is governed by the length of the cable, the aerial that's hanging off it, if you like. It's a bit like FM radio, but backwards. So if you have a cable of a known length with a certain type of circuit on it, it'll give you a set frequency. So as the cable length changes, the frequency changes. So by simply measuring the frequency of this oscillator, you can get some really, really good results. The only drawback is it's limited to a quarter of the wavelength, which works out to be about 60 meters. So you've only got 60 meters of cable, but you've got 60 meters of really good cable, whereas those other, TDR can be almost as long as you like.
Right.
And just to show a few results, these are, oh geez, how old are these? These are nearly 40 years old now. But really clean results. These haven't been, back in those days, it may surprise you, but we didn't have all this software that you could clean things up. We barely had a computer between us, but we did have one that we could print that out on. So these are really not filtered, not cleaned up. That's for a decoupled ANFO shot, so a lot more noise because the cable's not getting crushed against the borehole wall. This is quite clearly showing the run-up of 3,700 meters a second up to 5,100 meters a second. Again, these are my favourite traces. They're just so nice and clean. There's one that wasn't going too well, very much at the bottom, 3,800 up to 5,100. And this is a developmental explosive. Again, we're seeing changes in the in the way it was working. So these are really good results. The third technique is the other one that's probably familiar to a lot of people, is the resistive wire technique. Instead of having a time of flight, you've basically got a high-speed digital ohm meter that you're measuring resistance millions of times a second, and as the cable of a known resistance, as the cable changes, length changes, the resistance changes, you get a plot of resistance versus time, which you can change to distance versus time. And I'm sure you've all seen microtrap data like that as the pretty common side of things.
So are there, I guess, other methods, or is that pretty much run the gambit of everything?
Well, there's still methods around, the laboratory methods of, we talked a little bit about the street camera before, but the laboratory methods have probably progressed a little bit further, that we can use an ultra-high-speed video camera now to give us much better footage. Again, it's not in whole, but it's really good research material. So these are some of the frames that you can now get from a video camera. This is actually some stuff that Miguel Araros was doing on those hydrogen peroxide explosives, looking at how they were detonating. Great for reports, really good for finding out what's going on in those explosives, but probably not giving you enough information about anything that's in the ground. So these are more of a research tool. There's other things that are probably coming along that we've talked about a little bit before.
Yeah, so obviously you've been doing VOD a long time and have probably done all these methods. What do you think the future is moving forward?
Well, I like to think that some of the things that we've looked at when we were doing some measurements, and we're picking up some erroneous signals on some instrumentation, and we found that it was attributable to the EMP that comes off a detonating charge. So when a charge detonates, you get a lot of ions all rushing in one direction, and that with the laws of physics, it actually induces a signal. So you've probably heard of EMP pulses from nuclear bombs that'll wipe out everything and all our systems will fail. Well, this is just the same, but on a very, very micro level. So you can actually pick up these disturbances if you have the right antenna and you have the right sampling equipment on the shot. And you might say, well, so what? You can see a little blip go off. But so if we did some work looking at this with normal resistive wire, VOD, an initiation system, booster down the hole, an explosive column, stemming at the top. And we were just monitoring things, and then we found this noise on the channel that we were using to monitor something else. And lo and behold, that point there was when the booster fired. And then we got this increased noise, which corresponded to the explosive column detonating. And it continued to detonate. And then as the shock wave hit the stemming, we got another discontinuity in the noise. And we ended up with something like this at the end. And then if you have a look at the whole length of it, the stemming point, the initiation point, we know the length of the explosive column, and we can put it all together as the initiation point there, the end of the column's there. So now we've got a time of how long that explosive column takes to detonate. And so you can now get the velocity of detonation over that whole column. It's not, I guess you could look at it and say it's not continuous, but it's actually giving you information about how that explosive is detonating. And there's some things you can do to pull out a little bit more information about the quality of the detonation, as well as just its length of duration. And one of the, I guess, key things about this is, unlike any of the other methods which rely on a wire going up the hole to take the signal out to your box. This doesn't need any wire. So you can put any explosive, you can put a detonator in any position, a booster in any position, and you'll still get the results out. Whereas if you use other methods, as soon as that booster goes off, anything below it, you can forget it. You won't get that information.
Yeah, like if you have a top booster or something.
Yeah, that's right. Or you've got to put some safety boosters in or something like that. So that to me is where I think we're going. You know, it's tying in with sort of wireless things that are happening a lot in our industry. And I think there's a lot of other information we can get about the quality of the detonation in that thing. So that's where I am. That's a little bit of my history, what I've been doing in the last little while.
So I got one more surprise question for you, Alastair, before we move on to Tom. Do you have any interesting stories about measuring VOD that come to mind?
You're recording this, so I don't know that I have.
Can you say it?
I think probably how things have changed in the past. Because, like I said, we were able to go onto the local army range. We were able to take cardboard tubes. We were able to load them up with up to 80 kilos of explosive. We could stand them up, put our instrumentation in them and around them, walk about 50 or 100 metres away to a concrete wall and stand behind it and press the button and then giggle like crazy because it's just such fun. Whereas now, you've sort of got to do it, it's all got to be in a blast chamber or it's got to be in an underground mine and you're up in the surface and all the fun's gone out of it. Yeah. All the fun's gone out of it.
Yeah.
So that's, I mean, that really, well, there's another one where we're doing some testing on an army range, and we moved from cardboard to, it's actually the last time we were able to fire on that range, because we moved from cardboard to steel tubes, and the guys in the mess that was 2.2 kilometres away were a bit upset when a bit of shrapnel went through the roof.
Well, I could imagine, yeah.
It's amazing
no one's ever happy.
Amazing how a tube can open out and form this almost perfect aerodynamic shape that can then spin that far. And it surprised us all.
That's pretty impressive.
They didn't ask us back. I don't know why.
Okay, cool. So what we're going to do, thanks, Alastair, is we're going to have Tom Palangio come up and ask him a few questions, and then we'll open it for everyone else if you guys have questions. So, Tom Palangio.
Great.
There you go.
Thank you.
Welcome, Tom.
So Alastair's going to stay up here and maybe interject a couple times if he has something fun to say. So Tom, do you mind introducing yourself to everyone? Most people might know you, but...
Yeah. Well, I'm Tom Palangio, and I'm with Whipware. We developed a fragmentation analysis program. Alastair's talk brought back many memories of instrumentation in the explosives industry. My background, I worked for DuPont out of North Bay, Ontario, which was an explosives manufacturing facility. And I worked for field operations, and I worked for a technical service group. Ultimately, we were out of Wilmington, Delaware, the Eastern Labs there. And I was fortunate enough to work with a lot of very smart people. A lot of them worked on the Manhattan Project, and I learned a lot there. And it's interesting, you know, Alastair, you talk about the many ways to measure, you know, properties of explosives, velocity, detonation, density, you name it. But one of the very elusive things was what the explosives were meant to do. How do you measure the blast results? How do you measure fragmentation? And back in the 60s, DuPont was trying to do numerical modeling of blast results. And we hired a fellow by the name of Dr. Roger Favreau, and he was at the Royal Military College, and he came up with a numerical way to model a blast and predict results. And DuPont at the time actually paid him $1 million for a computer program.
That's a lot of money back then, isn't it?
Back in the 60s, that was unheard of. You know.
Yeah.
So then they said, how do we validate Dr. Favreau's work? And I had to go to St. Louis, Missouri, and we made a few blasts, and I actually had to sieve a blast. And if you've ever done it, you don't want to do it again. Because you've got hundreds of thousands of tons of material that range in size from elephants down to dust. And very, very difficult. Anyway, we'd shoot the shot, we'd put the scaffolding up, we'd sieve it. We actually took photographs, and they weren't digital cameras then when you took photographs. It was film, and it had to be developed and printed into 8 by 10. And so we had all this documentation. And we realized at the time what an arduous task it was to do this. And we were looking for an easier way to be able to quantify blast fragmentation. So I searched the world, really, and I went to Waterloo University. And there were a couple people there. One was Dr. John Franklin, and he was famous in his own right for geotechnical information. And Waterloo University themselves, they were doing a lot of enhanced imagery. They would take satellite images and enhance it in various ways and be able to identify underground aquifers and various geological things from satellite imagery. And John and one of his undergraduate students, Norbert Mertz, said, you know, I think we can take photographs of the broken rock and through various ways of enhancing it, be able to quantify some of the particle sizes.
I think you've got a picture of those guys, don't you, on the slides?
Yes, I think so. How do I work this now?
Hit the little arrow there on the, you know.
This one? Okay.
Keep going again.
Ah, yes, there they are. So the top one's is John Franklin, and the middle is myself. I had more hair then. And the bottom one is Norbert Mertz. He ended up teaching at, what's the name of the university?
Rolla.
Rolla, yeah.
Missouri S&T now.
Yeah, so. And we actually wrote that book, The Measurement of Blast Fragmentation, and we presented that at one of the conferences. But essentially what it was we would take a photograph and through an edge definition routine be able to determine the edge of each and every particle there and compute the areas and I'll put it in a graphical form. And it was reproducible. So all of a sudden, you know, we've got a way now of first validating blast models, because before that, you know, they could only be predictive. There was really no way short of, you know, sieving an actual blast to be able to give you that information. And so that's the way it started. And the routine in that was basically internal. We used it at DuPont, and it wasn't a commercial product at that point. So.
Okay. What were some of the challenges you faced when you started doing the fragmentation, and how did advancements contribute to the development of, you know, fragmentation analysis?
Well, in those early days, like I say, it was film. We would have to develop the film and we would have to process it. When digital cameras came out, that was a very important advance. I think Sony came out with a camera called Mavica, and it would actually take a picture and write it to a disc. That was a big, big breakthrough, you know, because we wouldn't have to print these 8x10s and put tracing paper in that, and I think I might even have a picture of that here. If I can find it. No. This is this is the way we would do it. You can see the vintage of the computers and everything else, but we would take a photograph, put it on a copy stand, take a digital image of it. We needed these digitizers. It was quite an arduous process even then. This is when I went to Missouri and was watching some of the material. We envisaged that every particle that was generated in a blast, instead of going out in the muck pile, we would wait for the trucks to bring it to us at the primary crusher. It was an ideal place to really measure everything. So especially when we started to develop things like digital detonators and that, when you were trying to get the magic timing, this was the way that we got a good representative sample. This slide actually shows you what you could do. So you see an 8x10 photograph on a copy stand with a video camera, and then you would see it on the screen. It would go through various edge definition routines and iterations. There was a lot of editing. Computers weren't as fast as they are today, and frankly, all of this was done in DOS, and things were pretty slow, but it was still much easier than trying to sieve the blast. So then somebody said, hey, we stop a belt every shift and we take a belt sample. Wouldn't it be nice if we could use your technology? When we stop the belt, we'll take a picture. We said, we can do better than that. Because cameras had been developed that would take pictures at fairly high speeds. In fact, you know, some of your high-speed cameras can stop bullets. You don't even have to stop your conveyor. We'll take picture on the fly and actually, you know, measure material as it's going, so we don't disrupt your production or anything like that. And we'll be able to tell you not only, you know, particle size distribution continuously, but even tell you in aggregate operations and that if you've broken a screen or if you've run off spec in some of your things. So technology was really our friend throughout all of these things, and technology was moving really, really quickly in that area. So that's that Mavica camera that I told you about. Again, it was just such a life-saving thing, because you would take the picture and it would write to a disk, and that was automatically digitized then, and you didn't have to use these frame grabbers, which are
Oh yeah. So, you know, it's not just a scientific pursuit, it has practical applications. So how has the fragmentation analysis field impacted the explosives industry, you know, in general, in the related sectors?
Well, it cleared up, I think, a lot of misconceptions. You know, there were a lot of theories out there as to breakage, and you know, there was a lot of different predictive methods. This actually kind of validated it, okay? The industry's always been very sensitive to things like adverse vibrations and damage to adjacent structures and everything like that. And pyrotechnic detonators always meant that you could only fire things so fast before you get scatter and cross-linkage. And we actually found that if we could shoot a lot of the shots faster, we could overcome some of these transient pressure effects, because you were measuring your velocities and everything pretty well under ideal conditions.
Yep.
But as soon as you actually put it in a blast array, you start to get these other things. You know, you get transient pressures, it affects the adjacent column, And all of a sudden, you're not getting that characteristic VOD anymore. So it starts to, you know, people start to realize what is really going on the bench. And so I think there were a lot of advantages going through there. We started to introduce micro balloons, you know, to get away from pre-compression, and you'd start to get the energy you actually paid for, you know, because it was operating under better conditions. So it was kind of ironic in a way that you were able to instrument everything that had to do with the chemistry of explosives, and yet you weren't able to measure the explosive results, you know.
Yeah,
So
which is what's actually, in the end, the most important thing, right?
Yeah, yeah. And you know, like, even from a client point of view, everybody likes to buy what they perceive to be the best. I don't know. Will high-test gasoline actually perform better in your car, or was it meant for regular? And in the explosives business, I mean, you want to maybe buy the best. You want to buy the best emulsion product. But maybe the blasting agent for your rock type and everything could give you the heave and the breakage that you actually wanted. So now you've got a way to actually quantify and relate, you know, to the value in use. So.
Yeah, and I think when we were talking about this before, you mentioned you used it with some microfracturing work too as well, and you have a picture of that in here too, I think.
Yeah, yeah. The one would think that the more energy you put into a blast, that the material is just going to keep getting finer and finer and finer. But that doesn't always happen. But sometimes you precondition that rock so you didn't actually break it, but you introduced microfractures so that when it does hit the crusher, it just disintegrates. So if you're monitoring amperage at a primary crusher, all of a sudden it doesn't take any energy at all to actually reduce the size. But if you're just looking at fragmentation on the bench, you don't exactly see it. Okay, so there's a bunch of things that can go on, a bunch of things that can happen there. This here is just showing. People ask us quite often, you know, where's the best place to monitor blast results? And some people go out in the muck pile, and you know, some people try and track it in different places. And some people are using drones and everything else. Theoretically, every particle that's generated in a blast ends up on a truck, and every truck shows up at a primary crusher. So we say that, and we've tried shovel cams and we've tried everything else over the years, but with every particle showing up at the primary crusher, we think we can theoretically see every particle that was generated in the blast. Because when it comes out of these trucks, it's not like a dump truck, it ravels out, so we get to see different layers of it. So if you're trying to evaluate digital detonators or something else, or get your timing right, or finalize a pattern, we can theoretically see every particle that was generated in the blast at that primary crusher. So I suppose in a way we're trying to remove the human element too. Because when we used to rove around with cameras taking pictures on the muck pile, people just tend to gravitate towards certain areas, or they're not fully consistent with the way they do it. But this way here, we get to see everything, and you're able to put numbers that are repeatable, okay? Like if we introduce a way to measure fragmentation, but it's highly dependent upon the operator. You might gravitate to something, you might gravitate to another. We need, for scientific method, we need something that no matter who uses it, we're going to end up with the same. And that's been our goal. Okay. So this is some of that microfracturing that occurs that you don't necessarily see with the naked eye. But it happens, and as soon as that hits the crusher, it just disintegrates. So. This just shows some of the applications that we get involved with. A lot of aggregate operations and a lot of mining operations. And you can see from the muck pile, I mean, it's just different parts of the blast have different types of fragmentation for various reasons. And it could be geology or it could be malfunctions, you know. So. But again, at least we've managed to capture the elusive thing, the unicorn, as my son calls it. And over the years, with technology changing, we can use drones now instead of going out in the muck pile. We can use iPads. Everybody carries a device. Everybody has an iPhone or, and these devices are extremely powerful and certainly convenient to use. So now you've got something in your pocket that allows you to measure your results. This just shows we put on courses occasionally. In fact, our technology is used by most major explosive manufacturers, and the use of the tool is actually promoted at most mining universities. It's part of the curriculum, and we've even the people that have made the sieves, the screens, which is the I mean, that's the standard. I mean, if you're in civil engineering or something like that, if you're measuring aggregates, you know, sieves are certainly the standard. But the Tyler Corporation and they've all adopted our technology, not to replace sieving, but just because our technology, by measuring it that way, allows you to detect problems immediately, you know.
Sure.
And it's ironic in a way, and we used to run across this early on because people were very skeptical about the technology. Is it going to be able to match sieving results and stuff like that? And in most cases, it did, but shape plays a part in that. So W.S. Tyler and these companies now, they will actually use our technology in order to specify screens and actually test screening. Okay, so it's an adopted standard now. And universities, most universities around are offering courses to use the technology in their mining courses. So.
Yeah. So we've kind of taken the same path that we took with Alastair's discussion on VOD, talking about, you know, how it was developed and how it's being used today. What do you see as the future of fragmentation analysis in the industry?
It's coming in more than ever, and will continue to. Advances in computer technology, artificial intelligence is really helping things along. The speed of computers and everything else is all adding to the ease of it. And you can acquire this now. I mean, if you have a device in your pocket already, all you have to do is get a subscription and you're in business. And really, even the explosives manufacturers, they're not even using it only for measuring blast results, but they're also trying to characterize ingredients. Okay, ammonium nitrate prills, micelles, there's all kinds of things that you can measure it. Basically, if you can image it, you can measure it. You can measure sphericity, you can measure size, you can do the whole thing. So it's really turned out to be a great tool and accessible to almost anybody.
Cool. So I'm going to end with the same question that I ended with Alastair, but you were prepped because you have a couple pictures to go along with this. But What are some interesting stories you have, or interesting applications of fragmentation, aside from mud pile analysis?
Oh my gosh, we've worked with the North American Space Administration. We work with various military groups. They utilize our technology for measuring the effectiveness of various structures that are supposed to be bomb-proof and everything else. We've used it. Companies come to us. A bread manufacturer came to us and wanted us to measure the bubbles in bread so that they could get even yeast distribution. One of the potato chip companies came to us and wanted us to measure their French fries. In the food and agriculture field, we measure stuff. Anything that you can image, we can measure. And there's applications in medicine. We can do cellular counts, and it seems like every time we open a door, there's 15 more doors behind it. So it's really something. And, I don't know what other pictures. It was so long since I assembled these pictures, but there's the Wonder Bread that was measuring the yeast distribution. This is a funny image, actually. We would put cameras on the back of underground tunnels in the underground mining, and sometime on the back shift, they end up tramming really large pieces of ore.
Yeah, that's a scoop bucket, isn't it?
There's a scoop bucket there, and we actually told them, we said, you're having difficulty. And the engineers said, no, you must be wrong. We can't possibly. Well, we had photo documentation to actually show that piece of oversize was much, much bigger than the scoop tram that was trying to haul it down. So we caught you. What else? Like I say, NASA wanted to measure some of the material that's on the moon because they're trying to create these rovers and that, and they want to make sure they don't get stuck, things like that. So we've worked with them. I guess I've run out.
I guess that's it.
Yeah.
Does now's a good time. Does anyone have any questions for Alastair or Tom? Everyone is speechless. We got a question back here.
So, Alastair, when you were talking about using antennas to start measuring VOD, obviously you can see the time that the blast starts, the time that it ends, you can get an average VOD across it. Is there anything that we have right now with respect to that is able to measure like run up or run down time to get more of a continuous trace going?
Sorry,
So I guess for the video, so for the recording, the question is,
Yep.
is there anything for measuring the run up and down time, basically?
measuring
Power
run up
column.
in an explosive column, you mean?
Yeah, with the antenna system you were talking about at the end.
Not really with that antenna system. That's looking at, I guess, the impulse coming out. You certainly can with, more conventional TDR or resistive wire, and that's very much dependent on the speed of sampling. But no, that at this stage we can't do anything other than do an average VOD over that. But certainly, I think there's an awful lot more information in that signal than we know at the moment.
We're still discovering, right?
Yeah.
Good question. Any other here? I'm just going to pass the microphone. That way, we don't have to repeat. I'll come down to you, Kyle.
Thanks, buddy. How close was the $1 million model to the actual sieving that you had to do for that entire blast?
It was pretty close. Dr. Favreau's model was it met a couple targets. But again, the validation had to actually be done. Nobody had ever sieved a blast before. It was all very, very theoretical, or it was obtained by means of modeling. And I think we were the only ones that ever sieved a full production blast. And it wasn't just one, we did multiple ones. But if you've ever done that, you don't want to do it too much. Favreau's model not only predicted fragmentation, but grade rupture and a whole bunch of other parameters. And he was, I won't say he was the first, but he was one of the real early ones that tried to do numerical modeling of blasting the way it was. So, but DuPont was happy. They thought they got their $1 million worth.
I'm still waiting for that size of a project.
Yeah.
I don't think it's going to come. Yeah. Any other questions? Tristan, here, let me get you the mic.
This is a fragmentation question. What are some of the common mistakes new people make when they're collecting fragmentation data?
Some of the common problems, well, when the system first came out, we used to need scales and things like that in the image to be able to relate to. That's all been eliminated now. But when we needed scales, people tended to gravitate toward the largest piece so that they could prop their scale up to it. And by doing that, they did bias the results. And when we started to go to time-of-flight cameras, we don't require scaling devices in there anymore. So it gives people a lot more latitude. And because the sampling size can be quite a bit larger now than it ever was originally because of the speed of things and that, we get you a much more representative sample, I'd say. But it used to be that people unknowingly or even sometime knowingly would kind of gravitate toward the larger pieces to be able to put the scale on and get fragmentation results from it. We really strove to get something that, irrespective of who the operator was, you should get the same results. And actually the drone stuff that people are using now, and it's so easy to use, gives you a very, very representative image, and it's good.
Any other questions? Yeah, Evan.
This is a fragmentation question on your mobile app. Do you see people utilizing that as a QA, QC method for their stemming to make sure that whoever's providing their stemming material, are they looking at that? That's what I wanted to do.
Yes, I think so. Most of the people now, want to be able to check. By checking your fragmentation and that, you gain a lot. You actually you find out if your explosives is up to par. You find out if your timing has been optimized. You find out if maybe even your geological assessment has been correct. Because all of these things start off as being assessments. So it gives you a kind of a balance check for the whole operation. And sometime, your explosive spec could be off. Sometime you want to tweak the timing. So at least this gives you a tool to know how to act and how to do things.
Good question, Evan. Any more? Okay, we've got one last thing. Since this is kind of a special event and these guys go out of their way they don't get paid or anything, it's
That's
just
not
their
what you
time.
said.
You're definitely not getting paid. So we try and make a nice little plaque for the guys. So to show our appreciation. Here you go, Alastair.
Thank you.
Yeah. Tom.
Thank you very much.
Okay, great. Okay, thanks everyone for coming. I guess the last thing too, you know, for the EP social that we did, you know, Evan did a ton of work on that. Pedro helped me with this, but we also want to thank the staff. You know, Adi's here, so you can share with the others. So thank you for helping us put this on. We really appreciate it. And thanks everyone for coming.
Okay, thank you.